So in our discussion of the development of an accurate model of the solar system, we've now reached a point where people have accepted the heliocentric system and accept that the Sun is at the center of the solar system. Problems that were produced by the fact that orbits were not perfect circles have now been fixed by Kepler's laws. Now, one of the things that Kepler's laws actually proved was that planets move in elliptical orbits, and in those orbits, when they are closer to the Sun, they move faster. When they are further away, they move more slowly. Now, this has been accepted by observation at this point. However, it took about 150 more years for this to be proven in science terms, in terms of what was physically going on. So here we're going to talk about that part of the story, about how the development of gravitation and the discussion of forces, motion and energy really tells us what's happening in the solar system. So here's Newton. This is the man that eventually solves the problem by coming up with universal gravitation. Now Newton, of course, was the man who the story is told about sitting under the apple tree when the apple falls on his head and Newton suddenly comes up with the great idea of universal gravitation and forces and energy. Unfortunately, this story is believed to have not actually been true and is one that's oft quoted just as an example of what gravity actually is. As such, I've hidden an anvil in this tree. And then finally, let's squash Newton with a piano. Now, even though it's Newton that comes up with the final theory of gravitation here, and in fact it's till the 1920s when Einstein updates it even further that it remains relatively unchanged, it was actually this man, Edmund Halley, the man of Comet Halley fame, who really was the one responsible for helping Newton to make this piece of scientific literature a reality. Now Halley was one of those true polymaths who did just about everything. He was an inventor, an astronomer, became Astronomer Royal. He was a physicist, a geophysicist, a chemist, a deep sea explorer. He was actually one of the first people to report inner ear trauma due to pressure changes when he was going down under the ocean in the bathysphere. He was a navigator, an explorer, an advisor to insurance companies, and is responsible for a lot of the early theories of annuity and insurance. And eventually, due to his exploration activities, was named by the Royal Navy as captain of the HMS Paramore and had his own ship. So Halley had a lot of different roles, but it's his function as the wrangler or the handler of Newton that we want to talk about here. And it was Halley who really went to Newton because he wanted to solve the comet problem that he came up with. Now comets were a subject of much discussion. Such things as meteors, hence the name meteor, being related to weather, even though meteors have nothing to do with the atmosphere and are actually dust and rocks entering the atmosphere and burning up, were considered to be atmospheric. No one was sure what caused the comet, and some people thought it may have been forms of cloud or lightning, when clearly these things aren't to us astronomical objects. And it was about this time in the 1600s that many spectacular comets appeared in the sky. Here's a picture of the comet of 1680 over Rotterdam, with people gathering in the harbour to observe this particular comet. Although people were now believing that that comets were actually astronomical objects and less that they were a product of the weather, a product of the atmosphere, people still could not explain why they occurred or what they were, and their appearance was often considered to be a very random event in the sky. And it was Edmund Halley who stopped and thought about this. In fact, Edmund Halley only observed the comet that his name is attached to once, in 1682, during his wedding night to Mary Tooke. here is actually a little dramatization of this particular event. Now bear in mind, comets do not do what this cartoon shows. Comets appear in the night for many nights over a period of weeks to months as they come closer to the sun and start to eject their volatile inner material. But the general spirit is here that Edmund Halley was outside observing the stars and saw his comet that would bear his name in the sky and stopped and thought, well, maybe this is a periodic occurrence. Maybe the comet is not just a random thing that happens in the sky, but maybe it's on an orbit about the sun. And maybe the same comet will return in the future many times. So the idea that comets were tied into the stars and tied into random occurrences was one that most people believed. Comets were considered divine omens, or sometimes a harbinger of doom. They were also thought to maybe be astronomical atmospheric anomalies, as I said, or astronomically single-time celestial events where a comet would appear in the sky and disappear. Halley said maybe the comet orbits the sun, and if so, did it behave in the same way as the planets, and would the same comet return on its orbit? And of course, this is where we could actually look at Kepler's laws. 150 years prior, Kepler had shown that the planets were travelling in elliptical orbits and were faster when closer to the sun and slower when they were further away. And he'd come up with p squared is proportional to a cubed. So we could actually predict the period of any orbiting object if we knew the size of its orbit. But no one knew quite why this was the case. Why did planets go faster when they were closer to the sun? So many people latched on to Halley's idea, and Halley himself did a lot of historical work looking into ancient texts and astronomical work of the past to see if a comet had recurred. Maybe a comet could recur with a common time over, say, 100 years, 150 years. So when you actually look back in the historical record and do the calculations, turns out people had seen the comet that was to be known as 1P, or Comet Halley, many times. The earliest recorded sighting was actually from the Greeks in 466 BC. The Babylonians recorded it in 164 BC and 87 BC, and Roman observations of 12 BC occurred. The Chinese Han Dynasty in 240 BC made a lot of observations of what they called the Broom Star. And here's some of their observations. Chinese astronomers actually have very long records of astronomical events and kept meticulous documents on changes in the sky. And here's a particularly florid picture of Chinese astronomers observing the comet in the sky. This is actually a much better picture than many of those that you see scientifically in terms of the comet in the sky. In fact, this is very much what Halley's comet does look like. So in terms of what Comet Halley is actually doing, it's a comet that's in a relatively short period orbit for a comet. Some of them are in shorter, but Comet Halley is known to repeat on a 75-year orbital period, and it's been doing so for at least 200,000 years. So the comet essentially is an inert snowball when it's out here on the edge of the solar system, and then as it comes closer and closer to the sun, it will eventually start to heat up and start to eject dust and gas. Here is the Earth's orbit, here is the orbit of Comet Halley. And you can see how eccentric this orbit is, meaning there's a big change in speed, and Halley's comet spends little time close to the sun and a lot of time further away. And here's an image from the last major pass of Comet Halley. It has semi-major axis on its orbit of about 18 astronomical units, so that's quite a big orbit, with an eccentricity of about 0.96. Its orbital period, and this was the thing that Halley was interested in, is about 75 years. The comet itself is very small. just 11 kilometers, with a mass of 2 times 10 to the 14 kilograms. Meaning it's really quite a small snowball-like object. It's only when it starts to eject gas and dust that it can stretch for very, very long distances across the sky. So the head of the comet is located in here, and this mess of gas and dust being ejected, mostly gas, is referred to as the coma, and this is the tail. So if we look inside Comet Halley, and the Giotto space probe has flown through the tail of this comet and photographed its nucleus or its head, this is what we see. Comets are actually very black on their surface, covered in lots of carbon materials, and then the white ejector that we see is caused as the comet heats up and the gases start to break out from the interior in geysers and shoot across the sky. So Halley wanted to look at this comet and predict its orbit. He wanted to know when this comet would return. But what they really needed to know to do this was, how did gravity really affect this comet? How could they really plot out the orbit of this comet? Kepler's law could predict its return, but we couldn't get good, accurate observations of its actual orbit, and calculations would be required to do this. And here is where things start to get a little complicated. While Halley was an excellent scientist, a scientist cannot be an expert in every single field, and his scientific discussions with others as he worked at the Royal Scientific Society started with Robert Hooke. Now, Robert Hooke in his own right was another very, very, very talented man, an architect, made very good microscopes. He was an artist, an engineer. He made a prototype respirator, which we can actually be thankful for given recent events. He was a biologist, a chemist, and looked into theories of combustion. Anybody who's done basic physics will have heard of Hooke's law, looking at the elasticity of materials. He looked at the physics of gases. He rebuilt London after the fire of London, and may have been the first to report Jupiter's great red spot from astronomical observations, giving us a long history of the existence of that storm on Jupiter. But one of the things that Robert Hooke was involved in was being a champion of the 1/r² law of gravity. Now, you might wonder why there's no picture of Robert Hooke. Here's his signature, and here's a big question mark. It's because of this discussion of gravity, and because Newton becomes involved in the discussion of gravity and the two do not agree, that there's no reliable picture of Hooke. After Hooke died, Newton hated this man so much that he had all of the pictures of Hooke removed from the Royal Society's gallery, taken outside and burned. So this was a very serious rivalry, and these two men did not get along, which you'll find is not unusual in the case of Isaac Newton. But Robert Hooke, while not coming out with this theory, was a big supporter of the idea of the 1/r² law, and people pretty much accepted that gravity was an inverse square relationship. Well, what do we mean by that? Well, if r is the separation of two masses in the universe, then the force that the force of gravity felt between those two masses will fall off as 1 over the separation of those two masses squared. So if we double the distance from a planet, then its gravitational effects will drop by 1/4. So the force of gravity is inversely proportional to the square of the distance from its source. So let's take Isaac Newton here and move him at different distances through space, something I'm sure Hooke would have been happy to do. Here he is at 1 Earth radius, sitting on the surface of the Earth. Now, weight is not really just a product of mass. Weight is a force caused by gravity, and your weight will be different on every planet you visit based on the mass of that planet. So weight is really a product of an acceleration multiplied by your mass, how much material you're made of. So sitting on the surface of the Earth here, our Newton is 623 newtons, because this is the unit of force that was named after Newton himself. So he's sitting at a radius of 1 Earth radius. He weighs 623 newtons. That's the force acting on him. Let's move to 2 Earth radii now. So twice the distance, twice the radius of the Earth away. Now he will fall off by 623 over 2 squared. So the force acting on him reduces by a factor of 4. So now he only weighs 156 newtons. At 3 Earth radii, Newton now weighs 69 newtons. And at 4 Earth radii, Newton is now only 39 newtons-ish. And this is an inverse square law. And if we plot this on a graph, this is how the force would diminish as you got further away from a gravitational source, such as a planet or a star. Now this created a bit of a problem because Hooke knew and was very passionate about gravity being a 1 over r squared rule, but they couldn't quite get the calculations to work. There was something missing when you tried to actually calculate numbers, and Halley turned to Hooke and wanted proof that 1 over r squared was true. And so Halley asked Hooke, please bring me the proof that 1 over r squared works, and let's mathematically determine the orbit of this comet. So Hooke really said, well, 1 over r squared is true, and Halley said, prove it. To which Hooke said, give me a moment, I'll have a look. Halley, being a little impatient, then asked Newton to have a look at the problem. Now, Sir Isaac Newton, as he was later in his life after these discoveries, was not the most easy man to get along with. He often had disagreements with people. He published his Principia, which is the seminal work on gravity, in 1687, and this work outlined all the laws of motion and gravity that we really use today. Again, another man who did experiments in everything. He was a very good mathematician. He looked into the nature of colour and light, optics. He invented a type of reflecting telescope and its mount. He invented a type of calculus, a mathematical technique, and was as per many other scientists of his day, was attempting alchemy, actually transmuting different types of metals one into the other. So taking something like lead and making it into gold. Their properties are very similar, and he was a supporter that you could essentially transmute or change one metal into another. This isn't as silly as it sounds, as this was a branch of science of the day and many prominent scientists were involved. Newton also did a number of dangerous experiments that I do not advise that you try. Lying on his back and staring at the sun for hours to attempt to see detail in it, and then having to go and lie down in a dark room for several days with a terrible headache. It's miraculous his eyes survived that particular experiment. Not done with his eyes, Newton would take a bodkin, which is actually a long type of knitting needle, and jam it behind his eyes in an attempt to try and generate different colours. I think he probably did generate different colours, primarily red. So I would not advise anyone to try this. He was interested in the nature of light, and he was attempting to see if the eye itself was responsible for generating colour. Eventually, in his later life, Isaac Newton became Warden of the Mint and was actually charged with looking up forgers and hunting them down and stopping people from forging coins, of which he hung many of them. Not personally, but sentenced them to hanging. But Newton had some very, very important contributions to make to science, despite all his various shortcomings. And Newton was tasked by Halley with coming up with some viable theory of gravity. So Newton went to Halley went to Newton and said, we need to solve this gravitational problem. To which Newton said, yeah, I've kind of already done that. And Halley said, can I see it? And Newton said, no, I lost it somewhere. It's in my papers. I can find it. And Halley said, I would really like to see this. So Newton looked for it and said, I lost it. So you'll just have to wait. I'll do it again. So Newton came up with this. Newton's law of gravitation. Every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. something we kind of already know. But calculations wouldn't work. There was something missing. And that thing that was missing was this g. So this 1 over r squared part of this equation people knew. Here are the masses. This would say be the mass of the sun and the mass of the comet they're interested in. But g was the thing that was missing. A number which makes this calculation work. Otherwise, it's kind of worthless. And it was Newton that came up with this. And that meant he had to invent a type of calculus. And the type of calculus here, this is a mathematical technique, essentially for finding areas of graphs. And here's a really almost a picture from something like a romance novel or something here of Newton at work in his study. I'm sure it wasn't nearly quite this nice, but still, here is his telescope at the back, and here's a perfectly coiffed Newton doing his work and thinking about apples falling from trees. But Newton came up with a way of differentiating and integrating a type of calculus. I say a type because Leibniz in Germany was also working on a type of calculus, and the calculus that we use today in mathematics and science is more based on the German Leibniz method than Newton's. But both are equally valid and both methods work. So Newton invented his own mathematical method and came up with that value g, the 6.67 times 10 to the negative 11. And they decided they had to publish this. Halley was incredibly happy about this. It meant that they could take this number now, plug it into the formula, and start predicting his comet. But first, they had to really publish this work on gravity, this incredibly important work on gravity. Now, unfortunately, Newton himself didn't have the money to publish this particular piece of work. So Halley went to the Royal Society, of who he worked for as a clerk, and asked could they publish this through the Royal Society. To which they said, no, we don't have any money. We blew it all on the Historia Piscium, a book on fish. We don't have the money to publish this. So Halley decided to publish it himself. Now, interestingly, if you have access to a copy of Historia Piscium, it's actually worth more than Halley's first edition work, because they took, once again, these copies of the book outside and burned them, because apparently people needed heat sources more than scientific works at this particular time in history. People could not sell this book, and so all of the money from the Royal Society was blown on this book, so Halley decided that he would pay for the publication of Newton's work himself out of his own pocket. To add insult to injury, later on, when the Royal Society was running out of money, they actually couldn't pay Halley his wages and paid him in copies of De Historia Piscium. So Halley had a lot of copies of this book lying around in his house and probably never went short of firewood. Now, some of the other things that were going on during this period were that the universities for a while were also shut down due to the Black Death, or the plague as we would call it now. Some people have been pointing out recently to me that Newton did his best work while the universities were shut down and he wasn't lecturing. I would like to point out that Newton did not have a computer and didn't have access to Zoom, so when Newton went home when they shut down the universities, he had little else to do but research and think. Now, we still just carry on almost as normal, just with Zoom going on. But gravitation was published. Halley made it happen. He wrangled Newton. He managed to get Newton to help him out. Newton was a man who was, as I said, very difficult to work with and to cooperate with. But somehow Halley had a great relationship with him, and the two worked well together, and they managed to publish gravitation. With Newton's universal gravitation out, they could now start charting the orbits of comets. So this particular theory now allowed calculations and predictions to be made for any orbit whatsoever, and really opened up the science of celestial mechanics. of looking at the gravity of the different planets and calculating complex orbits. So they immediately used Newton's gravitational theories to chart the orbits of 24 different comets, and discovered that 3 comets seen in 1531, 1607 and 1682 were exactly the same object, and that this comet orbited the Sun and passed close to the Earth every 76 years. With this prediction made, and people having a lot of faith in Newton's work here, decided that, well, now we need an observation. We need to wait the 76 years between predicted occurrences of this comet and see if they were right. Unfortunately, Halley did not live to see the return of his comet, and he died in 1742, 16 years before his comet returned. Halley, ever the patriot, said this before his death: "If the comet, of course, if it should return according to our predictions, impartial posterity will not refuse to acknowledge that this was first discovered by an Englishman." What Halley didn't know, because he had died, was that Charles Messier, a Frenchman, was the first person to actually see the comet return and to report this back. But it was still a big achievement for science. Gravitational theory worked. Now mathematics could be used to predict the position of an object and predict its orbit, and it could be done accurately, and our observations could then match it. So now we're into a new world of not just observing something and then explaining it, but theorizing the existence and the position of objects and then looking for them by observation. So Halley, and indeed Newton, was correct on all counts. The comet appeared in the sky on Christmas night of 1758. And it was hailed as a big triumph for scientific reasoning, and of course for Newtonian physics in general, which is absolutely true. And this was a big achievement in terms of physics. The French astronomer Nicolas Louis de Lacaille named the comet in Halley's honour. So while Halley was quite the Englishman and wanted to really push the discovery for Britain, it was the French that really made Halley's name for him, which is rather ironic. And here is a copy of what's referred to as the Gentleman's Magazine from May 1759, which talks of detractors of gravitational theory quite harshly, in a statement such as, "By its appearance at this time, the truth of the Newtonian theory of the solar system is demonstrated to the conviction of the whole world, and the credit of astronomers is fully established and raised far above all the wit and sneers of ignorant men." And that's really how it was reported, that people had no way to look down on Newtonian theory and gravitational ideas anymore. Now, it should be noted that it was really work such as Kepler's that started this hundreds of years prior. And indeed another famous scientist, Albert Einstein, later wrote that he was not happy that someone like Newton would give any credit to someone like Hooke. So Newton wrote to Halley that he wouldn't give Hooke any credit. Also, Newton never really referenced the work of Kepler either, on which he was really basing a lot of his own work. But Newton's theory of law of gravitation even was now firmly established, and we've talked through this before, and they could say with confidence that every particle in the universe attracts every other particle based on a 1/r² relationship, where g, this gravitational constant, ruled this equation and made this calculation work. So now, when people talked about gravity, they looked at it in a different way. Mass is now the quantity of matter, how much material something is made of. A weight now is a force which is acting on a mass. So it's a mass times an acceleration, F equals ma. and objects should be weightless when they're in freefall. So here's Newton's law of gravitation. If we take two masses, they could be you and another person, they could be you and the Earth, it could be the Earth and the Moon, the Sun and the Earth, anything. Any two masses in the universe will attract one another. Their distance r, and they will have a force towards one another. If we look at the directions, that'll give a positive force and a negative force from m1 and m2 respectively. But these two masses will feel an attraction to one another that will fall off as 1 over r squared. So this was now fully confirmed, that the further away you got from a planetary body, the lower force you would feel, and that it would fall off essentially as a factor of 4 as you went away from the planet. Now generally when we talk about gravity, we can ascribe signs as to whether something's attractive or repulsive. Gravity is always attractive. Two masses will always pull together and will not repel one another. Think about taking the poles of a magnet. If you take two magnets and stick them together, they will stay together and they will attract one another. That's because the north pole is attracting the south pole of the magnet. If you put two north poles together, they'll repel. Put two south poles together, they will attract. So here, the forces on Newton are attractive. He's going to be attracted down to the Earth with a force that is going to be a mass times an acceleration. However much material he's got here times gravity. Now, Galileo suggested this experiment, but there's no proof that Galileo himself ever did it. And that's to take two masses up a tower and then drop them. This experiment was done later on, but not by Galileo himself. And two balls, essentially, mass 1 and mass 2. If mass 2 is bigger than mass 1, the prevailing idea pre-Newton, and indeed pre-Galileo's experiment here, was that both balls would not land at the same time, and that the heavier of the two would land first. This is not true, and you can prove this. Try this for yourself, with obvious planning permission, and make sure no one's underneath if you intend to drop two heavy things. But if we take two masses here, and we drop them from the top of a tower at exactly the same time, one heavier than the other, they will land simultaneously. They will hit the ground at the same time. And that means the acceleration due to gravity is invariant with mass. It doesn't care if something weighs 10 tons or 2 pounds, it will still fall at the same rate. So here we have a coyote throwing a safe off of a roof. After 1 second, its velocity will increase by about 9.8 meters per second, or about 10-ish. So after 1 second of falling, its velocity is 10 meters a second. After 2 seconds, it's about 20. And then eventually it'll hit the ground. But one of the other things that was now discovered was that all falling objects on Earth accelerate at 9.8 meters per second. Don't worry about air resistance or other effects, but everything will fall at this particular rate, no matter what its mass. So on Earth, the gravity of 9.8 meters per second means that your speed increases by about 10 meters per second for each second that you're falling. Now mathematically, not that you need to memorize any of these equations, this is kind of why. We know that the force due to gravity, if we drop a ball on the Earth, is g times the mass of the Earth times the mass of the ball over r squared, which essentially would be the height of the ball above the ground. Newton's second law that he came up with, because Newton had other motion laws, is F equals ma. So what we can do is say, well, if the force of gravity is gmm over r squared, where this is the radius of the Earth, then the force on the ball will be the mass of the ball also times the acceleration of the ball. That puts mass on both sides of the equation, and it cancels out. So the rate of any falling object really just depends on what the mass of the Earth is, and essentially how far away you are, and that'll give you an acceleration. So ball that's 2 pounds or 3 tons will fall at exactly the same rate. And that's a common misconception amongst many people. So now what we have is the idea that mass is the amount of matter that you have in an object, how much stuff you've got, and the weight is the force that's acting on it. And this is going to have some very significant effects. If you go to different planets in the solar system, you'll feel different amounts of weight. Your weight will change depending which planet you are on, while your mass will remain the same. So your mass is the same on every planet, but weight will change. People in orbit experience weightlessness. That's free fall. The gravitational field is still present, and in fact is almost as strong as it is at the surface of the Earth. It's just that when you're in orbit, you're essentially falling towards the Earth and missing it. But let's take a look at gravity on the different planets. Here are surface gravities for the solar system. Remember, here's the Earth, and we're going to normalize this to 1. So 1 here is 9.8 meters per second, and is really based on the mass of the Earth, how much stuff the Earth is made of. And we've already talked about which are the biggest and smallest planets in our solar system. But here's Mercury, quite a dense world, even though it's quite small. And it's sitting here at about 0.4, so about 40% of Earth's gravity. So you'd feel kind of light on Mercury. Venus, almost the same size as Earth, very much a sister planet in terms of mass and structure. Venus is about 0.91, so very similar values here to the Earth. The Earth, of course, everything will fall, gaining at 9.8 meters per second for every second it's falling. Now let's go to Mars. Even though Mars is bigger than Mercury, it's not a very dense world. It's actually quite a bit smaller than the Earth as well. So Mars actually has a very low gravity. Now, one of the reasons its atmosphere is nearly all carbon dioxide is because all the lighter stuff, like hydrogen and helium and even oxygen, couldn't be held onto by the planet Mars. It all bled off into outer space because it wasn't heavy enough. It wasn't sufficient mass to be held onto because Mars's gravity was so low. Very few science fiction movies actually get the gravity of Mars right. If you watch any of the more popular movies, gravity is the one thing they always miss. And scientists, well, astronauts, if they were on the surface of Mars, would actually bounce around. Not as extremely as you see pictures of people on the moon doing, but they would actually have quite a spring in their step with quite a low gravity. Now Jupiter through Neptune, these planets here are gas giants, and these are the gravities believed to be at the top of their atmospheres, as there's no ground really, and well, there may be some solid material very deep down, but you'd never get to it. These are the gravities at the tops of their atmospheres. Jupiter, biggest planet in the solar system, about 2.6. Saturn, now surprisingly, Saturn is a very big world, second biggest planet in the solar system, but its gravity is only 1.1, very similar to the Earth. This is because Saturn is not a very dense world. It's very rarefied and is more the density of wood. Something you can often tell kids is if you have a very big bathtub big enough to float a planet, you could drop Saturn in and it would float like a block of wood. Uranus, again, same deal, not very dense, 0.88, Neptune around 1.14, so very similar to Earth gravity in these three cases. And then you've got cold and tiny Pluto out on the edge of the solar system. I'm not going to argue about the fact that people say it's not a planet. We're including it because it's there and it's still an extremely interesting body. Probably more interesting now since probes have been to it than it was before. And this has very small mass and a very low gravity of 0.05. So if you want to figure out the acceleration due to gravity on any of these planets, take the value of 9.8 and multiply it by this number. And this was an experiment that was proven by Dave Scott on Apollo 15. and he performed Galileo's experiment on the moon. He took a hammer and he took a feather and he dropped them and they fell and landed simultaneously. Both of them fell at the same rate. Now, he wanted to do this experiment on the moon because doing it on the Earth doesn't work as well as you'd think. So if you take a hammer and a feather and you drop them at the same time, the effect is that the feather will experience air resistance and it will actually travel on the air and fall more slowly than the hammer, which will just essentially pierce the air and land onto the floor. On the moon, this was more easily done because there's very little atmosphere to speak of. So you can find this video online where he drops the hammer and the feather and they both fall at exactly the same time and hit the ground at the same time, proving that Galileo was right in the 1970s. Now, as I said before, gravity is still acting in space. If you go into orbit, you're not floating around because gravity is no longer acting on you. When you're in orbit about the Earth, you're essentially falling, but just missing the ground, and perpetually falling the whole time that you're in orbit. And so weightlessness is actually an effect of constant free fall. It's not that the mass of the astronauts is now absent, and it's not that the gravitational source, being the Earth, is not acting on them. It is, but they're just missing it as they're falling. And we can prove this by simulating weightlessness on Earth. If you take an aircraft and you fly in what are referred to as parabolic trajectories, we've already discussed the nature of a parabola, you can fly upwards and then you can fly downwards on your trajectory. What this will do is, as you're accelerating towards the Earth here, you'll actually experience a period of zero gravity where your acceleration is essentially cancelled out by the acceleration of the aircraft. And this will result in moments of weightlessness. So you can experience weightlessness in 30 to 40 second bursts using this method. And this is one of the things that was done by scientists for astronauts to see how they would adapt to zero gravity conditions before going into space. The aircraft that performs this is the KC-135, what's referred to by NASA as its vomit comet, due to the fact that the sudden changes in the inner ear can sometimes cause people to scientifically vomit. If you wish to actually experience this, not the puking part, but the actual zero gravity part, a ticket to do this costs about $6,000 to do it privately. I've never actually managed to save the money and not spend it on something else, but I would like to try this, and you get to keep the snazzy flight suit. So as I said, gravity is still acting in orbit. You're not actually weightless, you're just missing the Earth. So armed with Newtonian gravity, this really opened up the solar system. Suddenly people calculated the mass of the Sun from the Earth's orbital period. You could also say, well, what's the mass of the Earth? And you could calculate this from the orbital period of, say, the Moon, and much better later once we had an orbiting artificial satellite. So we have very accurate measurements of the mass of other planets at this point. You could even use, say, Galileo's observations of the rotation of Jupiter's moons to actually guess now, or say guess, calculate accurately the mass of Jupiter. So the mass of Jupiter could be calculated just from basic observations. So Newton's gravitational theories really opened up the solar system in ways that we hadn't really thought of before. So what about orbits? We briefly discussed orbits there. Well, orbits, of course, will not spontaneously change. The moon will not suddenly fall out of orbit and land on our heads. If we launch something and put it into orbit, then in order to change its orbit, we have to change the energy of that craft in some way. So an object, once we put it into orbit about a planet, can only change its orbit if it gains energy or loses energy. So one of the things that Newton's discoveries allowed us to do was start to think of the solar system and start to think of gravity and mechanical systems in terms of exchanges of energy. Not so much as forces, but how much energy does something have? And the types of energy you really encounter when you're talking about objects moving around are potential energy, that's energy that hasn't yet been released, and kinetic energy, energy associated with the motion of an object. So take a ball and put it at the top of, say, a slide. It will have gravitational potential energy. It'll have a specific height, and that energy will be its mass times its gravity times its height. As the ball rolls downhill, it will give up that gravitational potential energy and it will gain kinetic energy. It will gain energy in terms of the movement of the object. If you then roll the ball back up the slide, you will end up with a situation where it gives up that kinetic energy and gains gravitational energy again. So we can start to look at mechanical systems. We can start to look at planets in their orbits in terms of energy exchanges. And that means we can revisit Kepler's laws. And this is the real explanation of what Kepler was discussing. Kepler said that when a planet was closer to the sun, it went faster. When it was further from the sun, it went slower. Now, with Newton's physics, we know that as the planet comes closer to the sun, it gives up its gravitational potential energy, essentially rolling downhill and getting faster and faster and faster until it reaches a maximum speed when it's closest to the sun. Then as it moves away from the sun and goes further out into space, it loses that speed and sacrifices it in terms of gravitational energy. So when we talk about our orbits, which we've already discussed previously, we can see satellites, be they natural or artificial, in a range of orbits. And we can put artificial satellites, such as communication satellites, into any range of orbits that we need. Higher orbits work well for such things as communication satellites, which bounce signals around the planet. Lower orbits might work for spacecraft which are either sampling the atmosphere or attempting to take images of the planet itself. So we've seen these before, and in our terms, here's our closed circular orbit. Here's an object going round and round and round in a constantly repeating orbit, as we discussed when we looked at Kepler's laws. Now, this orbit will have a specific energy associated with it. This spacecraft is moving, so it'll have a kinetic energy, an energy associated with its speed. It will also have an energy associated with gravitational potential, which will essentially be, from Newton's calculations, gmm over r. So how far away it is from the planet determines how much gravitational potential energy it has. Now, what does that really mean? That means if we want to put something into an orbit, we can fire it up using a rocket. That rocket has obviously a lot of energy on board, hence the huge flame coming out of the back, and that energy is being converted to gravitational energy. So if something is in orbit, you give it a little bit of energy and you can push it into a higher orbit. You can increase its kinetic energy and it'll go into higher orbit. Take away some of that energy, it'll demote into a lower orbit. But give it a lot more energy and you may allow the object to completely escape from the Earth. So it means that orbits cannot change spontaneously. If we're going to change the orbit of a spacecraft, we have to balance up the kinetic and gravitational energy. The total orbital energy is the sum of these two. We can't really do much about this, but we can put rockets onto our satellites and increase or decrease their velocity, bring them down or putting them into a higher orbit. So if you increase the speed of a satellite, what you'll essentially do is push it into a higher orbit. So here, this spacecraft has an energy of gmm over r squared plus 1/2 mv squared. If we give it more mv, we can't change m, but if we give it more v, we can push it to this higher orbit. So by increasing the speed of a spacecraft, we can get into progressively higher and higher orbits. And if you watch movies such as Apollo 13 or documentaries on, say, the moon landings or anything to do with the space shuttle and the history or the modern or the new space capsules, you'll often hear people talk in terms of delta V. And that really is acceleration, changing the velocity of an object, putting it into a higher or lower orbit. So if we give this spacecraft more velocity, we can push it into the high orbit. If we take velocity away by firing thrusters in the opposite direction, we can bring it back down to a lower orbit. But if we give a spacecraft enough energy, we can put it into a hyperbolic orbit. We can send it out into space, never to return. Now, historically, when we think about our spacecraft, something like the space shuttle never even possessed enough thrust to reach high Earth orbit. It only really went into low Earth orbit, and technically wasn't even outside the exosphere, so wasn't even really in space by some definitions. The Apollo Saturn V, the huge rocket that sent people to the moon, did have sufficient thrust to leave Earth's orbit and could actually go to the moon. Of course, it had to lose mass to do this, and that makes our calculations much more complicated. That's why rocket science is often referred to as being a difficult subject, because it actually turns into systems of complicated differential equations. But at its core, what you're really doing is increasing the velocity of your spacecraft. So an object requires a certain energy to go into orbit. Give it a little more energy, and you'll push it into a higher orbit. Give it a lot more energy and you'll throw it out of orbit and it'll fly off into space. And we've already discussed orbits a little bit, the difference between parabolic and hyperbolic orbits and closed orbits. If an object gets enough energy, it will go from a bound orbit, which is a repeating orbit like an ellipse or a circle, to an unbound orbit where it can fly off into space. And there's a specific energy that's set out for this, and that energy translates to a speed. And this is one of those things that is worth remembering, that Earth's escape velocity is 11 kilometers per second or 40,000 kilometers per hour. I remember things in kilometers per second. So this is 11 in meters per second, I apologize. So this is 11,000 meters per second, or 11 kilometers per second. And the escape velocity is dependent on the mass of the planet. So every planet you visit will have a different speed that you have to beat to completely escape from it. So take something like the Earth. We launch our rocket, we get enough energy to put a rocket into orbit about the Earth. And it's in a relatively low orbit. If we want to put it into a higher orbit, we give a short, low energy burn on our rocket engine and it pushes our rocket into a higher orbit. So here's a nice elliptical orbit that this rocket is in. Now if our engine is powerful enough and it's carrying enough fuel, we give it another burn. We fire the engines again, and this time we hit escape velocity. We go 11,000 meters per second and we will leave the Earth and not return. So this is just a little application where you can look at the escape velocity or the orbital velocity and actually see that it's actually independent of mass. So here we have a ridiculously large cannon on top of some very exaggerated mountains. And here we have a big fire button. If we have 1 kilometer per second value, we can fire a cannonball, it will crash into the Earth. Let's increase the speed. Let's go to 5,000 meters a second. Reload the cannon and fire. We'll still crash into the Earth. Let's change the mass. What we should see is no actual change in the trajectory or path of the cannonball. Now let's increase this to about 9 kilometers per second. If we fire the ball at this speed, the ball will now go into orbit about the Earth. We've given sufficient energy to the spacecraft to shoot the cannon at the back of the head, essentially. But we've given sufficient energy to this ball to put it into a nice, stable orbit. Now, if we increase our speed to 11 kilometers per second and reload and try again, what will happen? Well, at exactly 11,000 meters per second, the spacecraft or ball that we have launched will not go off into space. It'll go onto a very, very long orbit. That's because we're at 11 kilometers per second. Now, if we exceed 11 kilometers per second, this is the value that we need to beat to get away from the Earth. So any speed greater than 11,000 meters per second, and our spacecraft or cannonball here will escape into space, never to return. So 11,000 meters per second is the speed we need to exceed in order to get away from the Earth. And this is indeed what was done on such missions as the Apollo missions to the Moon. And here's the Apollo 8 lunar orbital plan. And as you can see, there's lots of different points marked on this plan. First of all, the Saturn V rocket was launched into space and went into orbit about the Earth. That's where it says insertion here. At this point in orbit, they would do checks, and then they would fire their rockets once more, and they would actually separate here from the command module with their rockets firing full power, and they would leave the Earth and they would go to the Moon. Somewhere along this line here, they would cease being they would get closer and closer to the Moon, and the Moon would take over as the major gravitational source and start to attract them. So they didn't have to fire engines the entire way. They only had to fire their engines briefly and enough to escape from the Earth. As they came into Earth orbit, into lunar orbit, they would have what's referred to as translunar injection, and then they could go around the Moon and then go back to the Earth, using the gravitational effects of the Moon to return to the Earth. A happy coincidence is this is Apollo 8, and the trajectory of their orbits follows the figure 8. I hope you enjoyed this brief discussion of energies and planetary orbits and how we can calculate gravitation.